I'm Erik. I'm senior hardware engineer at Grovf. Currently, I'm working on Rocky V2 architecture and design, not the graphical one, I guess the chip design one. So first thing first, I think even at this moment, there should be a question like how are these two spheres connected? I mean the machine learning, AI, and the chip design. So to answer this question, we should dig into the history of machine learning and understand like what were the pushers for this sphere, mainly besides the great minds of working. Oh, I guess it's the key that kills everything. Okay. Besides the great minds that are working in this sphere. So let's start. So this is the overview of the whole speech. So we're gonna talk about like why we need GPU clusters in this sphere. I mean the machine learning or the AI. A small introduction to what is RDMA and Rocky V2. The problem we are trying to solve here, the main problem, the definition of the problem, and a possible solution to it, or an open problem that needs to be solved here. So here in this graph, this is actually an interesting graph which shows the history of, we can say, like the AI, where the x-axis is, the points here are the publications in this sphere, and the x-axis is the date which these papers were published. And on the y-axis, we can see it's training compute called flops. This is basically, we can call it like, in reality, it's number of operations with float decimal points. But in reality, we can say it's like the size of the models. And because these papers are the ones that have real value, we can say like having more compute, bigger models means that the industry is going up. So what's the purpose of this? So if we have a look on this, we can see like we have three sections here. It's called the pre-deep learning area. It started like in 1952, the deep learning area and the large scale area. So here is the first interesting moment that happened like in AI. It's around 2010 where like the real deep learning era has started, because the idea of that started way back in the I don't know, maybe 18s. But at this moment, we can say like it started the deep learning area. It's because of around that age, at that time, NVIDIA has created GPUs that were much more powerful and had more memory. Which means that it was possible already to train these kind of models, like big models where there are multiple hidden layers. It started to be possible to train these kind of models like 100 times faster, or I don't know, 200 times faster. At this stage, we can say like it started the deep learning area. So the next interesting things happens here. It's about, I don't know, 2015, I guess, where the size of the models became like really big. Which the reason behind this is actually there are basically two reasons here. One of them was also the hardware. So the hardware already here at this moment supported like clustering, connecting multiple GPUs. So they act like one, I guess. And the second one here, there were a lot of models that were already designed to be like this big. For example, I don't know, at this era started the GPT, the GPT-4, which are like crazy big models, which needs like, for example, the GPT. I don't remember 3 or 4. There were used about 15,000 GPUs connected into one, plus about 300,000 nodes, which included CPUs, data points. I guess it's called like data points. So, looking at this graph, we can see like the trend is going up, and the problem here is actually that in order for research companies, not like the Google, the big ones like the Google, I don't know, DeepMind, in order to be on the float, to have to even test these kind of results, it needs to have like really big clusters, which costs a lot, which I think it's the main problem here. So, so what's the solution here for the scaling up the GPU clusters? So adding GPUs and GPUs, how they are connected. Today's solution is the InfiniBand RDMA. So we should have a look on it. So what's the point of this? Having this RDMA. So first, we should have a look on the TCP, like the simple TCP connection, which is connected through simple Ethernet. Ethernet is like the internet we are using on daily basis. So it's connected to Ethernet. The problem here is that it actually works, but the problem here, the main problem here, is that, as you can see, we have these buffers here. So each time when data needs to be sent, the data is copied many times. So first from the application to OS, and OS to network card, and send it through Ethernet, and also copied. This adds a lot of latency. Like in really like good network cards, it can be like hundreds of milliseconds even, which adds latency, and the bandwidth is hard to keep up the line rate. So if, for example, we are if the network card is connecting, I don't know, for 100 gigabits, it's really hard to keep up the 100 gigabit because there should be a lot of CPU involvement or GPU involvement. So the problem here is solved with the RDMA. RDMA stands for remote direct memory access. What it does, for simplicity, we can say like the application says the hardware send this data to another node, and that's it. So there is no copying of the actual data, which saves a lot of latency, and it's easier to keep up the bandwidth, so keep up the line rate of the to keep up the line rate. So one may ask that, okay, we have a great solution here. What's the problem of this RDMA? As I already taught, the problem is the cost of it. So as here we can see, like, it's called TCP/IP. Here it's called RDMA. In order to RDMA work, it needs its own specific hardware. So if you are using, for example, these LAN cables, we are using normal switches, routers. Here in RDMA, it's called InfiniBand switches, InfiniBand routers, which are not compatible with the standard Ethernet, and they cost maybe, I don't know, 2 times or 3 times more. So here is the problem that becomes like crucial in terms of the cost. So what's the solution here? There is a solution. It was done around, I don't know, 20 years ago. It's called RoCE. RoCE stands for RDMA over Converged Ethernet. So here the main thing here happens is that this application wants to send data to this one. So they are doing the same RDMA transaction, but they are using the standard Ethernet ports. So this solves both of the problems. The problem of copying, so there is no copying because it's doing the RDMA. This is solved, and also as it's going through the Ethernet, the problem of the compatibility is also solved here. So we can dig into the Rocky a little bit more. So we can see like this is the standard RDMA flow, this is the Rocky one, and this is the Rocky V2. This management is actually the switches and the routers that are used in the system. As we can see, this InfiniBand management, so InfiniBand devices, they cost a lot. Here so we are just putting the payload in the standard Ethernet and sending it through the air. And also there is a Rocky V2, which works on the application level. The standard is actually the Rocky V2 here now, or either RDMA or Rocky V2. So, in conclusion of all of this RDMA, what we have, either like RDMA or Rocky V2, they are doing the same thing in terms of users' perspective. So we are offloading CPU or GPU usage through some hardware. So it helps like the latency and the bandwidth. So also here we may think like, okay, we thought RDMA is good, but it has a problem of the cost. Rocky V2, that's the solution to like scale up, but it has another problem. So this is the problem that we are trying to here is the novelty that we are trying to solve here. So let's say we have like this big cluster of GPUs, also CPUs connecting to it, some storage devices that are also connected, and they are working as one, we should think of it like one unit. So they are connected with these switches, and let's have an example of this problem to understand what can cause a problem here. So the problem here is the congestion. So when, let's take an example. So let's say these nodes are connecting to switches, and all of these link speeds are the same. So the speed of these links are the same. So it means like, I don't know, 100 gigabit, or it's 100 gigabit connected infrastructure. So let's say these two GPUs want to read from this storage. What could happen here is that both of these GPUs can access this storage with this wire. But as we have already seen that, as I've already said, that these line speed are the same one for all of them. That means that if here is 100 gigabit, 100 gigabit, here is also 100 gigabit, here is also 100 gigabit, which means that here we have a congestion. So it means that either we should like do flow control here. So say like this, say GPU 1, do not send this kind of traffic. I cannot support it. But looking here, also we can say like we have this path here. If GPU 1 would connect like this switch and go there, we would not have this problem. So this can be the solution here. It's actually the simple case, you may think, but the problem is here that at real time we don't know actually. At real time, we don't know actually the state of this graph. So where the packets are flowing, the data flow, we don't know about the data flow. So actually, the thing is, this problem is starting to appear after about 1,000 nodes. So when these GPUs, CPUs, and storage become more than 1,000, this problem becomes crucial, and the overall latency and the throughput of the overall architecture becomes lower and lower. And the solution here is actually quite interesting, as here, if we are doing like the Rocky V2, so we are doing the hardware implementation of it. As we are doing the hardware implementation, there is a big problem here that we cannot put a lot of algorithms and custom algorithms. It's really hard to do like in hardware, do custom algorithm for each of the use case. So here the solution is that we are here from each of these nodes. We are generating statistical data about the whole architecture, so the whole, let's say, data flow. So using this data, it's becoming possible to solve this problem. So if we could use that statistical data, we can actually build this graph, understand where the data is flowing and how we can change. Because from hardware perspective, we have a way of changing the path where it goes, so how it goes. So we have from here and here and here, we have a way telling the switches, so there's a communication between the switches. It's a hardware part, but there is a way to say like this switch, send with this path, send with this path. So using this statistical data, it's becoming possible to solve this congestion problem for more than 1,000 nodes. I guess that's the whole presentation. So if you have any questions, I'm glad to hear. I hope I can answer them.
So I basically want to understand, again, what you're trying to solve. Basically, as I understood, you compare two setups. One is like the traditional setup where you have different nodes of GPUs, different nodes which interchange data through Ethernet via the network interface, and which is slow, you claim, compared to a setup that you suggest now. But here I'm not sure that I understood like how it exactly works. So it somehow skips the network layer in the OSI. So it basically tries to.
You mean here?
No.
Or the RDMA part?
RDMA part.
Here.
Even back one more. Yeah. No. Maybe one. Yeah. Basically.
This the TCP.
So yeah, this is the traditional setup, and what do you skip? Like First, what RDMA is again, and how does it work? I didn't get it. So how it physically works? It's still, I guess, a cable between two.
Yeah. RDMA is like it's really similar to the standard Ethernet that we are using, but it's a different standard. So it's not compatible with Ethernet. So how it's working? An application just sends this device with some API called verbs API. It sends the device and sends a request saying like copy this data from this application to this application. And the main thing in RDMA is that in the TCP connection, the data is copying to, I don't know, operation system and goes multiple layers. Here, the device is copying the data actually from the application space, which helps there to like minimize the latency.
From the application space, you mean from the in-memory?
Both the memory of the GPU, CPU. Also, there can be storage units connected to it, so it keeps the copying part. Basically, the main thing, the difference here is that it keeps the copying part. So you can like, I don't know, read from other device, just saying like, I want to read from this address, and that's it. So there is no overhead. They're connected to like copy is here. So it's actually all of that is handled with the device. It's actual hardware. It's done with actual hardware. So it's done with hardware.
You design this hardware?
Huh?
You design this hardware?
Yeah.
I have a question. So you said that you need to. So every application that want to work this, utilize this approach, should implement this API, the RDMA API, and you should write a logic how it should copy the memory to other clusters, or it's done automatically?
So it really depends on the application. So in here,
for example, I'm developing a Python application which do some computation. So do I need to add the logic about everything you tell now, or it will do automatically?
Okay, let's say this way. Here at this stage, so the application is using the device through a standard Linux API called Verbs API. I think it's possible to use the Python to like do the transactions, but it's on the transaction levels. There are also applications that work on RDMA. So basically, most of the users are using that applications that are working on the RDMA or Rocky V2. There is no difference that much. So there is even an application which sends these TCP packets encapsulated in RDMA. So it's working even faster that way. So when we like encapsulate the whole TCP packet in the RDMA packet, also that encapsulated in Ethernet packet, and it works much faster than just doing this TCP connection.
So if I have an application which uses TCP, I don't need to modify or my application.
Yeah.
I can just enforce it to taking.
Yeah. It's just a standard socket implementation which works on RDMA.
And have you tried it on an actual, let's say, deep learning training?
We can try it, or
have you tried it?
Me personally, no, but I know that it's actually used quite a lot. So for example, even in GPT-4, it's used like the RDMA is the main architectural solution for connecting this kind of like GPUs, CPUs, storage devices. As I've already said, for GPT-4, I guess, or 3, they are using 15,000 GPUs, which are connecting with this RDMA solution. Also, plus it's also there is also connected 300,000 nodes, which includes CPUs, storage devices, and a lot of devices, which are connecting to the same network. So this is a standard that is used in high-performance computing.
Is it also the setup in popular cloud vendors?
Yeah, it's the same solution. So this is actually the main way of connecting different nodes in like supercomputers or hyper clusters. This is the main standard that is used there. InfiniBand RDMA.
Are there any other questions?
Okay.
Thank you very much.
Thank you.